Welcome. The subject of this video is photodiode-based MOSFET commercial DC relays. I'm your host, Lewis Laughlin. Please visit my website at www.bristolwatch.com. This is part of about a dozen or so videos exploring different ways to use optocouplers, switching transistors, and various forms of power relays and input circuits. I'll give you a brief review of photodiode-based MOSFET circuits, and then we'll look at the some commercial units that are available that are reasonably priced. Once again, a photodiode is simply a p-n junction, normally used in the reverse bias mode. We use it as a sort of a miniature solar cell. When we shine light on it, it produces a small voltage. In the case of mine, I measured 0.43 volts. If we put a series of these photodiodes, if we put them in series, plus to minus, anode to cathode, like a solar panel, the voltage will gradually increase. Now, this is very low power. You're not going to be lighting up light bulbs with it, but we have another very important use for this. This is the VOM 1271 photovoltaic MOSFET driver. I discussed this in another video, but reviewing it once again, it's a series of photodiodes and a gate turn-off circuit. According to its spec sheet, it can produce up to 10 milliamps at 8.4 volts. Not a lot of voltage or current AI power, but plenty to drive a MOSFET. Here's another type of photovoltaic MOSFET drivers. One of them is a single driver unit. This is the PVI 5050N and the 5080N. And the PVI 1050N. These are made by International Rectifier. It does the same thing as our VOM 1271 does. In the case of the 1050N, we have two emitter units and output unit pairs. As an example, I'm using a PVI 5050N to drive a IRF 630 MOSFET. This diode, by the way, is internal to the MOSFET. When the LED is turned on, it generates a voltage of about 7 volts between the gate and source and switches on the MOSFET. This MOSFET has a rating of 200 volts at 6 amps, I believe. This gives us an enormous advantage that I can separate the gate drive circuits away from the high voltage drain source circuits. Here we are again, same circuit. This time I have included a DC voltage of 120 volts. Here is my load. Doesn't matter which side of the load, which side the load is on. It could be on the negative side or the positive side. But again, light up the LED, 7 volts on the IRF 630 gate. It switches on, light bulb lights up. Note that this is a normally open solid-state relay, if you want to look at it that way. The MOSFET is turned off as long as the LED is turned off. This is known as an enhancement mode MOSFET. If we were to use a depletion mode MOSFET, notice the difference here and here. The broken line is an enhancement mode, a straight line is a depletion mode. When I turn the LED on and producing 7 volts on the gate, I turn the MOSFET off. So this, with no input to the infrared emitter, would be a normally closed circuit. The light will light up as long as the LED is turned off. Turn on the LED, generate a voltage, the gate shuts off the MOSFET. Alright, here's a commercial unit. It's made by an outfit called Cridom. They have a range of solid-state MOSFET output relays that runs anywhere from 7 to 40 amps up to 200 volts, or they have another range from 7 amps to 10 amps at 500 volts DC. These are all MOSFET outputs. This is the basic internal diagram. What do we have here? We have a DC input, we have a control circuit, we have dual infrared emitters, we have dual photodiode detectors. Here we have a trigger circuit, and we have an N-channel MOSFET. This is a normally open output solid-state DC relay. Because of the MOSFET transistor and its associated diode, you have to observe polarity. Pin 2 must go to the positive side of the DC circuit. Pin 1 must go to the negative side of the DC circuit. Note that the input is also 3 is positive and 4 is negative. Here's a basic hookup diagram, if you can see this. Always note that here's your voltage source, whatever it is. It could be a microcontroller, it could be a sensor switch, who knows, and a battery, but you notice the plus side goes to the plus input, the negative side goes to the negative input. It doesn't matter where you place the load. You can connect the load to pin 2 as long as you observe polarity, or you can connect the load to pin 1. If you have a magnetic load, such as a relay or motor or contactor, you will need this transient suppressor diode. So that's how you would hook this up. Observe your polarity. Observe the polarity of your load if it has a polarity. Observe the polarity of your power supply. And observe the polarity of the spike suppression diode. Like all optocoupler based circuits, the voltage on the input is completely isolated from the voltage on the output. This is another Cridom relay. In this case, it has a rating of 3 amps at 60 volts DC, has MOSFET output, DC control for input, and it's a normally open output. Your input voltage can be from 3 to 10 volts, so you could drive this theoretically directly off of an Arduino. Again, let's look at our internal wiring diagram. We of course have a dropping resistor and our infrared emitter. We have a series, again, of photodiodes that generates a voltage and a gate control circuit. And the output, once again, you have to observe polarity. Pin 1 is positive, so you're going to connect. This as shown. Now you don't connect both together. If you have the one up here, this is going to go to positive, and you assume that pin 2 will go back to negative. Or you can use circuit B. It goes from negative through the load. Watch the polarity on your load. Watch the diode. And then this can go straight back to the positive supply. Again, you can use the load in pin 1 or pin 2. Watch your polarity. And that's a simple introduction to MOSFET-based commercial DC relays. Please visit my website at www.bristolwatch.com, and this is part of, I believe, about a dozen videos on these related subjects. Thanks for listening.